Hello, I'll be going through with you the second part of electromagnetic induction. And in this segment, we will learn a new hand rule, Fleming's right hand rule, and we will also learn a new application, which is an AC generator. Now, before we start this segment, it's important to review what we have learned in the previous segment. So maybe you can pause the video and think of your response to my questions. Can you highlight what does Faraday law indicate, and also can you also think of what does Lenz's law indicate? And then another thing is look at the examples for Faraday's law and Lenz's law. Like for example, when there is a magnet that goes into a coil, are you able to determine the polarity of the induced magnet within the coil? Are you able to, how are you going to deduce the direction of the induced current flowing into the coil? So these are the questions that we have covered in the previous segment. So to review them, now pause the video if you need to review them. Now moving forward to this part, let us recap. In this chapter, we are producing electricity, and how we are doing so is we are using motion, we are providing motion to make a coil or magnet move within a magnetic field. And when we provide these two ingredients, which is motion and magnetic field, we will generate an induced EMF, and if the circuit is complete, a closed circuit, we will generate an induced current. And this is the part that we have to bear in mind as we move on into the second segment on how we can generate electricity using an AC generator. Now, Fleming has come up with a very easy way of combining Faraday's law and Lenz's law with this thing called Fleming's right hand rule. And basically what we use this rule for is to determine the direction of an induced current in a wire. And there can only be an induced current, we can only generate electricity when we provide the two ingredients. So the two ingredients, as usual, will be a magnetic field and also some sort of movement. So as you can see here, when a straight wire cuts magnetic field, when a straight wire moves in the magnetic field, there will be induced EMF generated, because there is a change in the magnetic flux, which is the magnetic field that the wire experiences. Nothing new, same thing as Faraday's law, except that in this case, we are working with a straight wire instead of a solenoid. And we can use Fleming's handy right hand rule whenever we see a straight wire moving and cutting some magnetic field lines. So again, for application, for problem solving, whenever you see a coil, usually we'll use the technique that I've taught you all last segment, which is Faraday's law and Lenz's law, and the guiding questions that I taught you all. What does the coil experiences, what is the change in the magnetic field that you experience, and if you want to oppose it, what induced poles will the solenoid take. So this is usually what we do when you see a coil. When you see a straight wire, it's a bit easier. We are also applying the same concept of Faraday's law, but it's all subsumed under this very handy Fleming's right hand rule. And when you use a Fleming's right hand rule, take note, use the same FBI acronym, that your thumb refers to the motion direction, your index finger represents the direction of the magnetic field lines, and your middle finger tells you about the current, in this case, the induced current that you are generating. So maybe take some time to practice your Fleming's right hand rule when you are generating the induced current using the example shown on the slide. So at the bottom right corner, you see this example that there's a wire and you are moving the wire up towards the top of the screen, and therefore your thumb is pointing upwards, and magnetic field lines that the wire experience is from north to south. So point your index finger roughly from the right to the left direction, and your middle finger will be automatically, of the right hand, will automatically be pointing outwards from the page. So your right hand should align exactly with the picture of the right hand in the example. So take some time to do this. Later on, checking with your friends if you need help to orientate your right hand. Okay, so right now, after learning Fleming's right hand rule, we can now apply Fleming's right hand rule onto an AC generator. AC stands for alternating current generator. In a while, you will see why the induced current, which is the electricity that we create, alternates between different directions. So the conversion of energy is pretty simple here. We are converting mechanical energy because literally you use something to rotate the coil. It can be your hand, or it can be some water or steam pushing a turbine. And mechanical energy is then converted into electrical energy. I'll reinforce this later on, but you can also see that in this picture there is something called a slip ring over here. So again, last chapter in DC motor we use we use split ring, split into half, so it's like two half rings if you recall that. Now in the AC generator we use two slip rings. If you look carefully, these slip rings are circular rings, and there are two slip rings here. This slip ring here always is connected to this side of the coil, and the other side of the coil is always connected to the other slip ring. That is where it differs from a split ring in a DC motor. A split ring in a DC motor receives different part of the coil's current. Okay, so some technical part to note is about these slip rings over here. And let's move on to the next slide. So over here we will rotate a coil using a hand, or in a power plant we boil water and let the steam turn either the magnet or the coil. So in either case, we are converting mechanical energy and making the coil rotate. And when the coil rotates and let's say AD cuts the magnetic field line, Fleming's right hand rule kicks in, and there will be induced EMF generated. If the circuit is complete, then induced current will flow and power up the bulb. Okay. All right, so let us go to problem solving and look at this example. Now, let's say we freeze the frame. The whole coil is rotating because we are manually rotating the coil, but let's just freeze the frame here. As you can see, there's this coil ABCD, and it's rotating to us, it's rotating in a clockwise direction. If you focus on AD, the part of the coil which is AD, just look at AD. I'll run you through for this AD. How do we get the induced current direction to be from A to D as listed here? Okay, so AD is moving upwards to the top of the page. So using Fleming's right hand rule, orientate your right thumb upwards towards the top of the page, or your iPad, or on the screen. Okay, next, the magnetic field lines is pointing from north to south. So taking reference to the screen again, your iPad screen again, the direction of magnetic field lines is from left to right. So your index finger must be pointing towards the right, maintaining your thumb pointing towards the top of your screen. And therefore, naturally, your middle finger of the right hand will point into the screen. It helps if you look at your screen top down. So if you put a screen onto your table, right, literally you just stand up and then you just look down at your iPad, and orientate your right hand that way. Alternatively, you take your iPad and put it vertically like how you are seeing the usual projector screen, and then you orientate your right hand that way. So with this, we can determine that by using Fleming's right hand rule that the induced current, in fact, flows from A into D. Okay, I will do one more example for this part of the coin, BC, and the conclusion is that you will have an induced current flowing from C to B. So therefore, let's try again. For the part of the coin CB, which is this wire over here, the direction of the force and the motion is downwards because the whole coin is rotating in a clockwise manner. So your right thumb point downwards towards the bottom of your screen, and the magnetic field line is as per normal, no change to it from left to right. So your right index finger must point towards the right, and then your middle finger is now naturally pointing out of the screen towards yourself. So therefore, out of the screen means from C to B. That is the direction of the induced current. So at this point, when the coil is parallel, you will have an induced current flowing like this. In fact, this is the maximum current that it can generate. Now, next up, once the coil rotates to being perpendicular to the magnetic field lines, there will not be any induced current at all. So when the coil is here, parallel to the field lines, the wires AD and CB, they are cutting the magnetic field lines. Literally, they are cutting many magnetic field lines. And therefore, since there's a cutting of field lines, there is induced current generated in AD and CB, as what Fleming says in his right-hand rule. But when the coil is perpendicular, it is like moving along the field lines. That means the movement direction and the magnetic field direction is the same, it's parallel. Alright, so remember when you're learning Fleming's left-hand rule for motor effect or Fleming's right-hand rule for generator effect, the moment any of the two vectors are parallel, you will not get the effect at all. Always remember this, whether it's for DC motor or AC generator. So in this case, the movement of AD is towards the right. The magnetic field line is also towards the right. They are parallel. No induced current at all. Okay, so remember this. So from this slide, you have achieved two things. Number one, you are able to deduce the direction of the induced current generated in the coil using Fleming's right-hand rule. And number two, you're able to see that actually this induced current changes from maximum over here to zero over here. Okay, so we will represent this using a graph from maximum to zero later on in the deck slides. Okay, so this is what we call an AC generator. Now, let's now continue rotating the coil. So now AD is on the other side already. Just now AD was on the left. So as you can see, we continuously rotate the coil in the same clockwise direction. So if you apply Fleming's right-hand rule, you will realize that the direction of induced current that you generate in AD now flows from D to A. Just now it was A to D in the previous slide. Now it's from D to A. I advise that you pause the video and then you practice Fleming's right-hand rule by yourself. And you should get your middle finger of the right hand pointing from D to A over here. Okay, if you need help with this, you have to call for your friends, or you catch me when I see you. Then I will try to force and orientate your hand. Okay, so again, notice that the direction of induced current in this part of the coil has changed. Just now was A to D, now it's D to A. Okay, so there's a reverse in the direction of the induced current. Hence, later on we will call this an alternating current. It alternates the direction, as what I've shown here. And again, when the coil is perpendicular to the field lines, meaning that the wires motion on let's say BC or AD, the motion of the wire is parallel to the magnetic field lines. Your motion and your magnetic field lines, these two vectors are parallel, you will not have any effect, and therefore there will be zero induced current. And therefore I've just shown you one complete cycle, one complete turn, one complete revolution, and what will happen to the induced current. So some details to note. Note the difference between slip rings and split rings in the DC motor. The slip rings, like what the split rings do, they ensure that the wires in the external circuit do not get tangled up. It allows for continuous uh, flow of current, and notice that in a AC generator, the induced EMF and the induced current goes from a maximum to zero to a maximum, and during the two maximum, the direction of the induced EMF and current is opposite to each other. Just now was from A to D, and then half a turn later is from D to A. Okay, how much energy and how much electrical energy, how much induced current you can generate depends on Faraday's law, which is basically the same factors: how fast you rotate the coil, strength of the magnet, and so on and so forth. Okay, here's a difficult but important bit for you to consolidate and sum up the previous two slides. The graph over here, the graph of the induced EMF or induced current against time. So like what I've shown you just now, when the coil rotates across one complete cycle from position 1 to position 5 is one complete cycle in a clockwise manner. You can see that the induced EMF or the induced current goes from a maximum over here to a zero when the wires AD and CB are moving parallel to the magnetic field lines. You don't get any effect at all. And then it goes to a maximum, but a reversal in the direction of the induced current, because just now current was flowing from A to D, and in position 3 current is flowing from D to A. So a reversal in direction, back to zero, back to maximum, back to zero. And this is the profile of the electricity that we generate, whether is it induced EMF, or when there's a complete external circuit, the induced current will flow with the same profile, same graph. So again, I'll reinforce Fleming's right-hand rule. Only when there's cutting, only when the straight wire cuts the field line, like what you have seen in AD in this position, then there will be induced EMF or induced current. When the motion of the wire is parallel to the field lines direction, which is like what you see in position 2 and 4, then you do not get any effects at all. Okay, so this is an easy slide because it's the same thing that we have learned previously for DC motor. The DC motor effect and the AC generator effect, both are same but different. Different because DC motor, you are creating motion, you are providing electricity current, and you want to create motion. In this chapter, generator effect means you are providing motion, but you want to generate out induced EMF or induced current. So that's the difference, but the similarity is shown on this slide. Whether is it in the example of generating electricity using a coil, or whether is it using a straight wire, Faraday's law comes in. So if you recall, Faraday's law tells us about the induced EMF and induced current, which is here. The magnitude is affected by the rate of change of magnetic flux that the coil experiences. I've unpacked this in the previous segment for this chapter, and these are the same points over here. We can increase it by increasing the number of turns of the coil, the length of the wire. In fact, if it's a straight wire, you might want to write this down: the length of the straight wire, the length of the straight wire that cuts the magnetic field line, that affects the amount of induced EMF. Copy this down and write this down. Using stronger magnets, turning it faster. So conversion energy is quite clear cut. The more mechanical energy that you input, and soft iron core, if you can position it within the wires, you basically create a stronger magnetic field. And again, the frequency of rotation. Okay. So over here, you can see the effects of the various factors on the output, induced voltage or induced current. Uh, Please note there is an error when I print the slide for you all. Look at the words at the bottom here. Notice that they are swapped. Okay, so I say again, please correct the error in your printing. We should swap over these two words. So this graph over here on the right refers to the effect of doubling the number of turns of the coil. So please make the change. There's an error in the printing. And if we increase the number of turns of the coil or increase the length of the coil, basically when there's more wires is longer, we will gen generate more induced EMF, like what you see in the red color graph. Because we do not turn the coil faster or whatsoever, the time axis remains the same. Okay, so this is the type of the graph. Now, this is another common factor that we change, which is what happens if we decides to turn the coil faster, like double the rate, double the speed, double the frequency. So when we turn it faster, there is a faster rate of change of magnetic flux by Faraday's law. So therefore, the maximum induced voltage or induced current will be higher. So if you double the rate, it will be double. So before that, it was at this value, as shown in the blue graph. But because we double the rotation speed, the induced EMF or induced current is not doubled. Right. Now, one more thing is about the time axis, because we now turn the coil faster at double the speed. Therefore, you notice that the number of cycles has now increased, has now doubled in fact. Previously, when we turn the coil at a normal speed, you can only see one cycle here and a second complete revolution here. So two complete cycles over here. Now, within the same time, from 0 to 2t, within the same time period, because you turn it faster, you can turn more rounds. So you double the speed means you turn double the rounds. So as you can see the first complete cycle is completed here, second complete cycle, third complete cycle, and fourth complete cycle. So now within the same time, because you turn it faster, you can turn 4 rounds compared to the 2 rounds previously. All right, so note this graph profile. All right, so right now we go on to some other details for the AC generator. In a simple AC generator, we rotate the coil, which is the wires, but we can also rotate the magnets instead of rotating the coil. As long as between the coil and the magnet there's some sort of movement, and the movement is not parallel to the magnetic field lines, you will get the induced current or induced EMF. So in reality, our generators, we rotate usually the magnet as shown in this slide. Why so? We can call it a fixed coil generator because we don't rotate the coil. We don't rotate the coil because we rotate the coil, we need to put in slip rings to ensure that wires don't entangle and so on and so forth. So it's a little bit more cumbersome. If we rotate the magnet, we avoid this problem completely. So it does not require slip rings or carbon brushes. We can make it into a smaller, more compact size, and less likely to break down because carbon brushes are prone to overheating and wear and tear. Okay, so this is an example of fixed coil generator, AC generator also, where we fix the coil, we don't rotate the coil, instead we rotate the magnet, and therefore the coil experiences a change in the magnetic field lines. The coils are also so-called cutting the magnetic field lines because the field lines are moving. So the magnetic field lines linking the coil change, and this is Faraday's law in effect, and therefore there will be an induced EMF generated in the coil. And because the coil is a complete circuit, therefore the induced current will flow through the output terminals. Now, checkpoint, some other variants of generator. So same thing, we fix the coil over here, as you can see, and we rotate the magnet. So explain how it works. This is how I'll explain the basically Faraday's law. When the magnet rotates, the coil experiences a change in the magnetic flux, and by Faraday's law, this sets up induced EMF and induced current in the circuit, in the external circuit. Now, part B, please take note. This is might be new to you. So again, remember what I say about the movement of the wire, and the vectors must not be parallel. If the vectors are parallel, then there will not be any effect. So in this case, if you apply Faraday's law, we will get the maximum EMF when the magnet is vertically oriented, meaning the north pole is up here, the south pole is here. I mean, or the south pole is here, the north pole is here. As long as the magnet is vertical, I want you to think about the rate of change of magnetic flux, as what Faraday say. And for the coil, when the magnet is vertical, we are seeing a sudden change. Just now the north was nearer, and after it goes past the vertical position, suddenly there's a complete reversal of magnetic field lines from north to south suddenly. And this only takes place when the magnet is about to go to a vertical orientation and then turn over the other direction. All right, so when the magnet is vertical, the coils will experience a drastic and maximum very big change in the magnetic field, magnetic flux or magnetic field lines, because the magnetic field lines changes from north to south. And this is a drastic change, a big change in the magnetic field, and therefore this is where the induced EMF will be the strongest. Now, on the contrary, when let's say the north pole is here and it's rotating horizontally, going past the horizontal position to a slanted position, well, the coil over here just experienced, well, it's a north pole, north field lines very strong, and then it gets a little bit stronger, and then it gets a little bit weaker. So the change in magnetic field lines when the magnet is horizontal is not so drastic. There's a change, no doubt, but it's not so drastic. Okay, and this is improved version of AC generator. So if you look at the two examples, two part B and part C, notice that now there are more coils, and basically that's the gist of the answer. So in the previous design, when there's only like two coils, there's a lot of gaps in between when the magnet rotates. So the poles move away from the coil that is facing, and therefore you sort of lose the opportunity to generate more induced EMF. So over here, when you basically to improve on the design, you just fill out the gaps with more coils, and then you connect all the coils in a parallel way, so that you can generate and so-called collect all the induced current that flows. Okay. So take some time to read the answer. I've also printed the answer for you. Okay. And that's it for this part. And you have basically learned number one, how to deduce the direction of the induced EMF and induced current when you have a straight wire in the generator that is cutting the field lines. I think that is the most important technique to learn for this part of the chapter. Again, second thing is not new. It's basically Faraday's law, that the idea of when the coil experiences change in the magnetic flux, there will be an induced EMF generated. If the circuit is complete, then the induced current will flow. So with this, please practice on the questions, and I will see you all in class.